So, my name is Burkhard Noltensmeyer. I'm the founder and CEO of Teutonet. So, this is my first talk in English. I'm a little bit nervous, but yeah, let's begin with. So, we are a hosting company from Germany. We do hosting since 20 years ago, and since 5 years we are operating hosting OpenStack, and since 2 years we are working with Kubernetes. And we are from the region Ostwestfalen-Lippe in Germany, in Bielefeld. And in our region there are very strong companies that are in the industrial control business. I just drop a few names. And I was always curious about machines and how they're working, so I was curious how to apply cloud native into the industrial domain. And in our region is also University Fraunhofer Institute, and they run a smart factory for integrating new concepts. And we reached out to them and applied for a research project. And here's a view on the factory floor. So they integrate all kinds of machines and technologies. And we set up a research project with them to monitor data from the industrial domain. And this leads to our mission statement: getting a sense what is going on and aggregate information with context in a distributed world. So this is a broad statement, and it's difficult to start with. And we choose the bottom-up approach. And the world is big, and there are a whole lot of protocols, and this applies also to the industrial domain. There are scattered locations, multiple factories, for instance. There are a multitude of protocols from several vendors, and over the years they are also changing. There's missing context. You might have only special data, but without an annotation which machine it is. And everything together is an overwhelming information to get along with. And for instance, I would characterize maybe two kinds of protocol. One is the binary protocol, which has only binary data but no formal meaning. So you have to add this meaning. You have to write custom exporters for them to use Prometheus speech. And you have to describe, okay, register 1 is the temperature, register 2 is the motor speed or something. And this applies to Modbus, which is a very old protocol. Profinet is a newer protocol. They have got a formal description for the data format, but unfortunately most vendors, when they give away a machine, they don't give away this formal specification, and you end up doing reverse engineering these protocols. And so this is one thing, to get these data at the proximity of the machine. So we've got one example. This is an electricity meter that we integrated, and it has got a serial protocol, and it had at least some context. You can get the serial number out of this machine to identify it. So this is very good, and also the data about wattage, what you need. And on the other hand, there are protocols like OPC UA. UA stands for Universal Architecture. This is a protocol that wants to solve more things. So they've got a discovery and a subscribe model, and they've got a security model. It is working on layer 3, so you can have like kind of SOAP requests. And this is more complex. In my opinion, it's maybe a little bit over-engineered. So one example is like a controller, and an industrial controller, like this, for instance, that we use in our climatization in our server room. So, and we needed edge devices for protocol conversion. So these buses, like these binary buses like Modbus, and are mostly only reachable in the proximity of the machine. So we have to extend our reach into the factory floor, and this is what we choose for. So there's these Raspberry Pi in industrial grade, And as you see here from the inside, there is a DIMM module with a Raspberry Pi in it. And you can apply this directly at the machine. And we need this as a foundation for our integration. So we decided to, we look at how we can do continuous integration with a Raspberry Pi, with the ARM processor. And firstly, we did run the CI runner of GitLab on the Raspberry Pi, but this was unbearable slow because the SD card in there is rather slow. And if you have a 200 megabyte image, it will take half a minute of decompressing. But it is possible to emulate ARM on x86, and there are containers. You can add QEMU inside the container, and then we were able to run our continuous integration for ARM containers on our x86 machines. And we were even able to set up a CI run which builds x86 and ARM containers in one row. So I think, and this will also be ever more important in the Kubernetes space because ARM servers are on the rise also, and so this will be more important in the future to have this kind of architecture integration. So we're still struggling with remote management. So we've got a whole lot of ARM machines out there, and we have to manage them. And we are not decided which approach to go. So there's open source software like ELIOT, which runs, which you can give containers to run remotely. Maybe we will go to the Kubernetes Federation road and put up a small Kubernetes cluster on each Raspberry Pi to leverage the Kubernetes Federation API in the future. And then we would be able to continuous integrate and continuous deploy up to the factory floor. So, now we have got this laid out this foundation, and then how to go further from that. So we took Cloud Native for the rescue, and taking Prometheus as a building block, and build microservices on top. With Prometheus, and also adding a control plane. So I will further dive into the concept. A few words for Prometheus. By design, I would say Prometheus has got a very powerful query language. It has got labels for adding context. It has got a very efficient design. It has got consolidation rules and alarm rules that can be executed along in real time. But also by design, Prometheus has no event processing, no sub-second resolution, no multi-tenancy, no receiving of data. So everything is scraped, but you cannot send it to Prometheus. So the first two, event processing and sub-second resolution, we can give away that, but we needed multi-tenancy in our platform, and we also needed the receiving side to overcome NAT gateway problems. So, and for the transport, we choose to go with the Prometheus format with open metrics. You may know this format already. So you've got the metrics on the left side, and then the labels, and then the actual amount, like 1027, and also timestamp, with is seldomly used. So we only use live data, so we leave out the timestamp. And then we decided to go with MQTT for the transport channel. So, and this is how it looks now. We have got our Revolution Pi with open metrics, which has got a small container on it with a Python conversion program, which manually has to be adjusted for each machine, and then we will send it to MQTT broker. This MQTT broker already runs in our Kubernetes cloud, and then we developed a little bit of glue code like MQTT to PROM to get the MQTT data to subscribe on this channel, and pretend a scrape endpoint for Prometheus to get the data into Prometheus. So might not be the most elegant way, but this is a solution that we come up with. And as you can see, so Prometheus pulls the data out of the MQTT PROM gateway. And we also set up a second channel to put these raw data into Cassandra. So if we need some special service or a special report, we can run this in Cassandra. So this is our data plane microservices. And then you've got a control plane to store the configuration data, so the MQTT channels and also the users for the broker and this kind of stuff. And the main thing that we developed is a bunch of REST APIs that is running these control planes and synchronizing the configuration to each parts. And on the left side, we have got these MQTT broker, which do kind of basic authentication about HTTPS. And on the consuming side, we have got Jupyter and Grafana. And there's no multi-tenancy in Prometheus and also in Grafana and Jupyter. So we run a bundle of Prometheus, Grafana, and Jupyter for each tenant. And then we to have a single sign-on, we implemented OpenID in front of these with a reverse proxy server. So each tenant can use their services with the same password. And in the front, we've got a Kubernetes Ingress server, and each tenant configuration has got its own host name under which directories then these services will be located. And the services can be consumed either with a browser, and we also developed a command line client with Golang. Here you can see the syntax of the command line client. So we mainly developed these command line client to be flexible and to also be on the Windows side. So with Golang, we can easily compile a Linux and a Windows binary, and we don't have to hesitate. And we can give this to customers for self-administration, so they can administer their accounts and their certain machine configuration. So this leads to the workflow then on the factory floor. So first, the tenant has to use an API user with a sensor path, with a Kubernetes, with a Mosquitto path to deliver the data. Then he has to configure his edge device with a certain configuration for importing their machines, like a register mapping, connected with the internet, and then he's able to configure the Grafana dashboard. So this is a little bit of manual configuration, and I think what we heard in the last talk to configure the Grafana dashboards and the Prometheus automatically will also erode. I think that we would like to go in this place to automate this process further and to have real continuous integration on that. So this is an example of our server room. This is a Grafana dashboard, screenshot of a Grafana dashboard, and we used a Mermaid for delivering this diagram on the upper part. So this diagram is generated programmatically with Mermaid, so you don't have to draw it somehow. And you see there's on the left side there's the temperature from the outside, so we've got free cooling, and then the temperature goes inside, and then we mix the air to prevent too cold air from going inside, and then we've got an air condition Klimaanlage, and this air condition can also be monitored. And as a result, we can see the temperature. And we also import open weather data to have a forecast to see what we might need. And you may know it with Grafana. You can run performance indicators inside of rules with it. So we have got power usage effectiveness (PUE), and we can generate that on the fly. So we see we have a total power consumption of 15 kilowatts, and the climate control needs 3, so we have around 1.2 up to 1.4. So this is one example to run this platform. So now we did a prototype with TensorFlow. This time we don't use a real machine, we use a virtual machine, so virtual machine out of our cluster. And these virtual machines also have certain characteristics, and yeah, we took 4 dimensions from a virtual machine, like CPU time, like written bytes on the disk, like network bytes receiving. And yeah, we took these data and splitting it into a training set and a validation set. And then we had a student doing his master thesis. He set up an LTSM network and trained it. And yeah, you can get these data out of Prometheus very easily. So you can do just a range query, and you will get the data back as a JSON object. And that's what we used with a bunch of Python scripts to get these training and validation data. So, and this is what it looks like. So the gray curve is the actual curve, and the red curve is the predicted curve. You might notice there are some gaps in the red curve. That's because we did the training sets for 5 minutes, and each 5-minute period is trained independently. So unfortunately, it doesn't mix very good. Yeah, you can see some similarities, but I think it's very difficult to get a real meaning out of it. And as Brian told yesterday, you need 18 months, or Google said they needed 18 months for getting real useful training data. So this is maybe 3 days of training data that we used to train it. So yeah, we thought the training is get valid predictions is very, very hard. But the other things that we accomplished along, so this cloud native journey and research project took us a course over 1 year, and but we gained confidence in the team with that the microservices are doable. And we discovered that the CI testing of microservices is very hard. So that's what we've learned. So you've got dependencies between the microservices, and when you want to test one microservice, you have to mock up the 3 other microservices to be able to test this one microservice. So this is hard. And yeah, CI builds of x86 and ARM contained in one run is very good in my opinion. And yeah, as I told, TensorFlow prototype, doing a prototype is hard, but it's doable. But getting valid prediction is very, very hard. So we decided to not go this road for the short run. Yeah, now I come to the end. So I've got some references to what we're using. So there's an exporter for the accelerometer available that we use also as a foundation. There's this Glue OpenID Connect server that we use for our implementation. So we tried DEX from CoreOS. We weren't able to get DEX running. We also used Keycloak, or tested Keycloak from Red Hat. Keycloak was okay, but we settled on Glue because Glue also supports single sign-on like universal second factor U2F, and yeah, OPC Foundation is the holder of this OPC industrial protocol. So this is what we used for our pilot. So thank you very much.